Hello, everyone. So today we're going to start lecture 13. So this is brand new material for the first class after spring break. So I'm going to share my screen with you and I'm going to go through some notes that I have prepared, and hopefully you've read through these notes, or maybe you're going to read through these notes. Here in these notes, you're going to see the breakdown or the table of contents of everything you'll find in these next few pages. So for today's class, we're going to start chapter 9. We only have 2 more chapters left to cover, but chapter 9 is one of them. So in chapter 9, I'm just going to give you some background information. We were in chapter 8. We were like in this unrealistic world where we knew something about, or everything about, the population, and we were imagining what the sampling distribution would look like. That's what we were studying before break. Now we're actually going to go the opposite direction, which is the realistic approach. So meaning that I'm going to take a sample, and from that sample I'm going to imagine what the entire population is like. This is called inferential statistics. So with inferential statistics, we have 2 different ways of attempting this, and chapter 9, which is confidence intervals, or CIs, is the first way. So today we're going to look at CIs for a population proportion. Remember, we talked about this and introduced this before break in chapter 8. My population proportion is denoted with the letter P, where before break we were talking about P hat, which is the sample proportion. Okay, and back in chapter 8, I told you that P hat is X divided by N, where X is the number of individuals that supported something or said yes to the question, and N is the total number of individuals in the sample. Now remember, individuals doesn't have to be people. It could be computers, or it could be houses, it could be cars, it could be anything, right? So don't think it's just always people. It's just a lot of times when we're doing these studies, it's people. Okay, so I'm going to look through these notes a little bit and give some information about the CIs. CIs are built around P hat. This means P hat is the center of my CI. It's my midpoint. So if I have my CI, which is an interval of numbers, I could find that center by using midpoint. Okay. The interval, we use an interval because P hat varies, right? Each sample should give me a different sample proportion. Okay, we've talked about this before in chapter 8. So since each P hat would be different, we're using an interval to estimate P. So P is my population proportion, right? So I'm using an interval of numbers to estimate P. Okay, so I'm going to say P is between these 2 numbers, and it's going to be a lower bound and an upper bound. And we're going to find out how to calculate that in a little bit here. The level of confidence is the proportion of intervals that will contain the value P if repeated samples are obtained. What we're looking at is it's the middle 90%, or middle 95%, or middle 99%. You can really use any percentage, but typically in this class we talk about 90, 95, 99. And these pictures here, you will see where we're looking at the middle 90%, or in this other example, the middle 95%. Okay, I want you to notice that it leaves this little area in the tails, we call this. In one of the group works before we left for spring break, you actually calculated these areas, and it's going to translate now into what we're doing. So we can see for this first example, if we're looking at the middle 90%, that we have 10% in the tails. Well, it's the middle, it's centered. So that means we have 5% in each tail, okay? The area in the tails is what we call alpha. And I do have that somewhere down here a little bit. And that value alpha, we divide it by 2 because we have 2 tails. So when we get to that, I'll mention that again. When we're looking at a confidence interval, it just means that when we have 90% confident, it just means that I have a certain number of values in my interval. It's a certain width, okay? If I move my confidence level up to 99%, it doesn't mean that I'm actually just more confident in my answer. It means that I'm going to include more values in my interval. I'm going to make my interval wider, so then I'm including more values in my interval, then I'm more confident in my answer, okay? I don't want you to think of a CI as a probability, okay? Because what we're calculating here is we're estimating P. P is something that has already occurred. P is a set value for a population. It's just we don't know what the value is. It doesn't change. When we're talking about probabilities, we're talking about the likelihood of an event occurring, and that's not what we're looking at here, okay? So I don't want you to think that. When we're talking about a 95% confidence level, that means 95 out of 100 CIs built will contain P, the value P, okay? It's just we don't know. So we don't know which ones will include it and which ones won't, okay? So that's why we say 95% confident or 90% or 99%. It really can be any percentage. Just those are the typical ones we use, okay? Here I have some notation. My p-hat follows a normal probability model with a center at p and a spread at the standard error of p-hat. Okay, I'm sorry, my center is at p-hat and my standard error at p-hat. We already did these calculations. We've looked at this notation for the last couple weeks before break. The standard error calculation is the same as before, except for now I want you to notice we're using p-hat in the calculation, not p. I want you to remember that when we talked about this before, that p-hat is the center of my curve. And before we used P there in that calculation, P was the center of my curve. Okay, so that all works together there. So I want you to see a picture here of this 95% CI curve. So there's no CI there, it's the curve showing the middle 95%, the centers at p-hat. Okay, here's my formula, okay? So my formula, remember it's an interval, so that's what the plus and minus represents. I'm going to take my p-hat, because it's the center, I'm going to add a value to it to get my upper bound. I'm going to subtract that same value from p-hat to get my lower bound. This value right here, my z at alpha divided by 2. Remember what I said, alpha was the area in the tails. I divide by 2 because I have 2 tails, it's the middle. This is going to be what we call the z-score, the z-critical value. All right, and these are set values for the certain percentages, and I will show you that here in a minute. And then, of course, my standard error calculation, which we already know.
What are you talking to? What are you talking to, Mom?
Okay, so I'm going to share the screen back with you guys. Okay. So when I'm looking at my CI calculations, here I have for the normal 3 that we use. For the 90% CI, our z-score value is 1.645. 95, it's 1.96, and for 99, it's 2.576. These are the z-score values for that correspond with the area being the middle 0.9. or the middle 0.95, or the middle 0.99. So here you can see for an example of the 95% CI and my curve showing. Now remember, now I'm on the Z curve. My Z scores means my center 0, my spread is 1. As you can see, the middle 95 is shaded, the center of my curve is 0, and my upper bound here for my shaded area is 1.96, and my lower bound is just the negative value of that. It's the metric, it's negative 1.96. Okay, so that's where those values are. When we're looking at CIs, we have requirements. So we've already talked about these before, where I need to meet normality. So I have n times p-hat times 1 minus p-hat is greater than or equal to 10. We've done this before break, but we had p in here. Remember, because our center of our curve was p, now the center of the curve is p-hat. So we should already have p-hat because we divide x divided by n. Okay. The second one is that the trials must be independent and sample size can't be more than 5% of the population. We don't need to check this. It's just something we assume. Sometimes I like to mention these because they do pop up on the homework once in a while. So number 1, we need to check for normality, but number 2, we don't need to check. We're just going to automatically assume that is true. Okay. Here's my interpretations for my CIs. So we are 95% confident that the population proportion of, now I'm going to talk about my variable or my context here, is between my lower bound and my upper bound. That's the only statement you need to include. Or you could talk about the second one there, that's here. With our calculators, so we can do this by hand, which I almost do it by hand all the time because it's just so simple and quick, or you can use your graphing calculator. So for mine, I go to stat test 1 proportion z interval. I have to enter an x, n, and my confidence level, so in a decimal form. So if it's 95%, I'm going to use 0.95. Okay. Let's take a look at an example. So for this example, I'm looking at 150 RIT students. 93 of them support a pass-fail grade option for courses. I want to estimate the population proportion of students at RIT who support the pass-fail grade option with a 95% confidence. So I'm going to go through some of these parts separately. Now, I might just say, go ahead and estimate it, meaning make my interval, right? Calculate the interval, which is part E, and then part D, and then maybe I would say interpret the interval, which would be part E, but I'm going to walk you through steps. Now, if you look on the next page, I have the completed example. So step by step, how I did each part. So what is the sample proportion? That's x divided by n. So it's 93 divided by 150, which leaves me with 0.62. What is the standard error? So it's the square root of p hat times 1 minus p hat divided by n. That is 0.0396. Is it safe to assume that the sampling distribution is approximately normal? So this is the n times p hat times 1 minus p hat is greater than or equal to 10. So yes, it is, because it's 35.34. So yes, it is normal. So I just indicate that with a little check mark and say yes, normal. Now to the actual calculation, I'm just going to plug in all my values into my calculation I have. Here are my z values of 1.96. My p hat's 0.62. My standard error is 0.0396. I already calculated those above, so I can just plug them in. So I get my CI to be 0.5424 as my lower bound up to 0.6977. So what this means is that we're 95% confident that the population proportion of all RIT students who support the pass-fail grade option for courses is between the 0.54 and the 0.6977. Now I have a follow-up question. So it's like a little different for us, as I didn't talk about this yet. Does the CI show that less than 70% of the students support the pass-fail grade option? So I'm going to answer yes, since the entire CI is below 0.7. Or you could say yes, because the upper bound is less than 0.7. So the key words here, and the question is that it says less than 70%. So when I'm looking at that, I want to make sure my entire CI is in support of this question, okay? So I'm looking for the entire CI to be less than 70%. So every number in my answer here should be less than the 70%. Now it can go the other way around and could say more than. I'm looking for greater than. So maybe the question is saying that more than 40% of the students support it. That would also be a yes, because every number in the CI, so in my interval here, is larger than 40%. So yes, that would be true. The only other one that's like a little tricky is if it asks if the population proportion is equal to a value. So maybe this would say, does the CI show that the population proportion is 0.60 or 60%? Then you would say yes, because 60% is inside the CI here, okay? But if it was, so if it wants to know if it's equal to something, you want it inside the CI. If it says less than, you want the entire CI to be below that value. Or if it says greater than, you want the entire CI to be greater than that value. Okay, I hope this helps, and I will be on chat very soon. Thank you.